Welcome to a new video in our series, A Beginner's Guide to the C Programming Language. In our last video, we discussed dynamic memory allocation and the memory allocation functions malloc, calloc, realloc, and free. In this video, we will cover a few data structures. A data structure is a container of data that organizes data in a particular sequence. The main purpose of data structures is to store and retrieve data efficiently, as well as perform operations like sort, search, etc. Please like and share this video, follow our channel, and subscribe for notifications on new videos. In this session, we will discuss a few data structures like lists, queues, stacks, and trees, and discuss how they organize data and the operations that are performed on them. It is very important for every programmer to know and understand data structures and algorithms. While we will not discuss any algorithms, we will talk about time and space complexity and the big O notation. As I said earlier, a data structure is a container of data that organizes data in a particular sequence. A programmer can create unique and complex data structures as required in their programs. You will understand how a data structure is organized and the operations you can perform on them. The data structures included in the video today are singly linked lists and some variations of the linked list like a doubly linked list, circular lists, queues, and stacks. Then we will go over the basic structure of a tree and discuss some of its features. As mentioned earlier, there are many different data structures, each with its own characteristics and benefits. Let's start with a list. The basic unit of any data structure is a node. A node consists of user data as well as any link information required by the data structure. When a data item is available to add to the data structure, a node is dynamically allocated and the user data is stored in the node. Then the link info is updated to insert the element into the data structure. A linked list is a data structure where each node is linked to the next node in the list. The node in a linked list is a self-referencing structure. That is, it contains a pointer to a node of the same type. In a linked list, this pointer refers to the next node in the list. Besides the nodes, a node pointer is also declared outside the list. This pointer can be given any name but is generally referred to as the root pointer. When the root pointer is null, it means that the list is empty. Otherwise, it will point to the first node in the list. Then each node contains a pointer to the next node. So using this reference, you can iterate through the list sequentially. The last node in the list will have the next pointer variable initialized to null. This indicates that it is the last node of the list. The typical operations on a list are adding a node to the end of the list. Here, if the root is null, then the root is initialized to the first new node. If it is not null, then you iterate through the list till a node's next pointer is null and initialize this next pointer to point to the new element. To remove a node from the list is a more complex operation because you can remove a node from the top of the list, bottom of the list, or in between the list. Here you need to initialize the relevant next pointers in the previous and the next node correctly. Also note that the node that is removed needs to be freed so that it is returned to the free pool of memory. Similarly, inserting a node to the top, bottom, or in between two nodes is also done in the same way. The list explained here is called a singly linked list. It can be traversed from the root node till the last node sequentially. A search operation will involve iterating through each node in the list, comparing data values till found, or you reach the end of the list. When a list is no longer required, you need to make sure that all the nodes are released to the free pool of memory. Otherwise, you will have memory leaks, meaning that you have allocated dynamic memory but have not released it. This is an important consideration when you are using data structures where you need to make sure that all dynamically allocated memory is released when no longer required. The slide shows two variations of a linked list. The first is a doubly linked list. It's an extension of a singly linked list which has a link to the next node of the list. A doubly linked list has an additional link pointer which points to the previous node. Also, in addition to a root pointer, it has a last pointer that points to the last element of the list. The feature of a doubly linked list is that it allows for reverse iteration through the list. That is, you can traverse both ways in a doubly linked list. Another variation of a linked list is a circular list or a circular buffer, where the next node of the last element of the list points to the first element of the list. In a circular buffer, you have two pointers: the head pointer, which points to the first element of the list, and the tail pointer, which points to the last inserted element of the list. Both the head and tail pointer moves through the list as you extract and insert elements within it. When head and tail pointer are the same, then the list is empty. An element is added to the tail, and then the tail moves to point to the next element of the circular buffer. Similarly, an element is removed from the head, and the head moves to the next element. A circular buffer is very useful in a producer consumer scenario where it is used to define a fixed length buffer that both the producer and the consumer share. Let us now move on to another data structure called a stack. As we know, a stack is a last in, first out buffer or a LIFO buffer. A queue is another data structure which is a FIFO buffer or a first in, first out buffer. Both these structures are types of lists. As shown here, a stack has a pointer that always points to the top of the stack. Then each node of the stack points to the next element in the stack until the last element of the stack, which will have the next pointer initialized to null. All operations in the stack happen at the top of the stack. The two commonly used operations are push and pop. A push operation pushes a new node to the top of the stack. The top pointer now points to the new node added, and the new node points to the previous top node. A pop operation removes a node at the top of the stack. The top pointer now points to the next node of the stack. Here the top node is freed and destroyed. A queue is a data structure that is a FIFO buffer or a first in, first out buffer. It contains a head and tail pointer that points to the start and the end of the queue. All removals happen at the head of the list and all additions to the tail of the list. Unlike a circular list that has a fixed number of nodes within it, a queue can change in size as new elements are added and removed. Now we learn about the next group of data structures, which are trees. A tree is a container of nodes which are ordered according to a key value. Just like a list, there are many types of trees depending on how the tree is organized. As shown here, a tree is an ordered list based on a key value of the data being stored. Each node contains two pointers, a left pointer and a right pointer. In addition, you have a root pointer that points to the top of the tree. When an element is added to the list, you need to first search the insertion point for the new element in the list. So you traverse through the tree starting from the root. Compare the key values of the new node and the tree node. If the key value of the new node is less than the tree node, then traverse to the left node of the tree. Otherwise, traverse to the right node of the tree. As you reach the last existing tree node, you can then insert the new node to the right or to the left of the tree node, depending on the value of the key. A tree data structure is very useful for performing searches because while a list is searched sequentially, a tree search splits the node with each compare into two parts, reducing the number of comparisons required to find the final node. An important aspect of a tree data structure is about balancing the tree. A tree can often become unbalanced, resulting in a lopsided structure that will reduce the benefits of quick search of nodes in a tree. So you will need to keep track of how balanced the tree is and keep the tree balanced at all times. This adds complexity to the implementation of the tree structure. As you can see, there are many types of trees. A simple tree can just have nodes in it organized like a tree without any attempt at balancing it. Other kinds of trees are trees that are self-balancing. You can also have trees that can have more than two nodes or store multiple key values in each node and so on. Finally, let's have a quick discussion on algorithms and the big O notation. This course is about a beginner's guide to the C programming language. A deeper discussion on algorithms is out of scope of this course. Look out for our next video series, A Beginner's Guide to Data Structures and Algorithms Using C. Please subscribe to our channel and click on the bell icon to receive notifications of these new videos. As we have seen, there are many different types of data structures, and each type has many variations. You need to understand how a data structure contains the data and the impact that these data structures have on the algorithms that you use on them. You may not need to know how to implement each one of them because depending on the programming language you use, there are inbuilt data types or libraries that provide implementations of data structures. For example, the standard template library in C++ provides data structures like lists, queues, maps, etc., as well as algorithms to search, find, and sort. Similarly, Python provides the same functionality using inbuilt classes. Obviously, when available, you should prefer to use the standard implementations rather than do it yourself. Finally, let's discuss a measure of time and space complexity of algorithms called the big O notation. When you have a small data set, you will not really be concerned about how fast your algorithm will process the data because with the powerful computers we have, it may not make a significant impact on the user experience. But as the data set gets larger, the impact of this increase on time and space requirements for the algorithm needs to be considered. The big O notation helps you understand this so that you can choose the right data structure and algorithm for the most efficient performance. The big O notation measures the efficiency of the algorithms. To calculate it, you need to analyze each step of the algorithm and the number of steps you are performing to get it completed. The end result is a time and space complexity function that will tell you how the algorithm will perform with respect to the number of elements in the dataset. For example, the time complexity function of O1 means that the size of the dataset has no impact on the algorithm. On means that the algorithm will increase linearly with the size. That is, if it takes 1 second to process 1000 elements, it will take 10 seconds to process 10,000 elements. On square is a quadratic time or space function. Here the time taken is proportional to the square of the number of elements in the dataset, and so on. The graph here shows the different time or space complexity functions. As mentioned earlier, as a programmer, you must be aware of the impact of the size of your dataset on the time and space requirements of your algorithm. This will help you manage the performance and efficiency of your application better. This is all we have in this session. We have covered a few types of data structures and some variations of each. We have also had a brief discussion on algorithms and the big O notation. Thank you for joining us. Please share and like this video, subscribe to our channel and register for notifications. In our final video in this series, we will implement a simple linked list. See you soon.